Hello viewers, welcome to Gurukul Live Lectures. I am Dr. Preeti Jagwani from Department of Computer Science, Aryabhat College, University of Delhi. Today I am here to tell you something about algorithms. Algorithm, it is a term which is with which everyone is familiar. More specifically, people from mathematical sciences are more familiar. So algorithm, technically speaking, it is a series of unambiguous instructions written in order to solve a particular problem. Let's say we want to solve a particular task, or we want to handle a particular problem. There is a step-by-step instruction plan to solve each and every problem. That step-by-step instructions is basically known as algorithm. So what is the essential condition for an algorithm? It must produce the desired output, and that too in a finite amount of time. Means it should be finite, and computer algorithm, as we consider, must be language independent. That means it should not be dependent on any language. It is language independent. It must have well defined inputs and outputs. Inputs and outputs must be very well defined. They are measurable, they are tangible, and the instructions must be unambiguous and clear. Now a field within the computer science comes which is about analyzing the algorithms. So why one need to analyze the algorithm? What is the need to analyze the algorithm? It is because we want to quantify the resources which an algorithm is consuming, which an algorithm is requiring. So what are the resources in a computer science domain, or in computer science domain, what quantities or what items we considered as resources? So basically computational time is a resource of primary importance. So how are we going to analyze the algorithm, that which algorithm is taking much of the resources or which algorithm is taking less of the resources? So analyzing algorithm is also required to identify the best choice when we have n number of variety or n number of algorithms to solve a particular problem. So we will be going with the algorithm A, or we will be going with the algorithm B, or we will be going with the algorithm C. That depends how costly one algorithm is in terms of computer resources. So that's why we need to analyze the algorithm. So what are the ways to analyze the algorithms? One idea could be of an experimental study to measure the efficiency of an algorithm. So here the idea is to measure the running time using CPU clock, and for a particular algorithm, let's say we pass different input sets. For each input set we are going to record the CPU clock time taken by that particular algorithm. So how about this idea? Limitations for this idea is, first of all, it is necessary to implement the algorithm. Without implementing the algorithm, we won't be able to measure the CPU clock time, and how many input sets we are going to take, because we cannot run a particular algorithm on infinite input sets, and for each and every input set, same set of hardware and software is required to run the algorithm every time. Along with that, let's say we have two different algorithms which are to be compared using this experimental study approach. So to compare these two algorithms, first of all, a same environment will be required, and it might be possible that for some inputs first algorithm performs better than the second, and for some inputs the second is performing better. Another scenario could be, for some inputs first algorithm perform better on one machine, and the second algorithm works better on the other machine for some other inputs. So this is going to create a complete chaos. So we cannot analyze, so we will not surely be able to analyze algorithms using this experimental study. Then a question mark comes up, then what is the idea then? How to analyze that? How to analyze the algorithms? So it requires an agreed upon model of the computation, and a model of the computation which is agreed to all the stakeholders should be agreed upon. Here a need is to adopt general approach rather than this experimental study, which should figure out the running time required by an algorithm, and that should be independent of any platform it will run upon. So in short, we need a model which is an independent platform independent model, and which is which is agreed upon by all to analyze the algorithm. So here comes into the picture random access machine RAM model. So RAM model is a model of computation in which RAM is a model in which analysis is performed with respect to some fundamentals. What are these fundamentals? What are these agreed upon ways in which RAM model is agreed upon? First of all, it is a generic model of computation. It is a single processor. We are not assuming a multiprocessor architecture in our RAM model. Then instructions are executed one after the another. We are not assuming, we are not having any concurrency here. We are not letting any concurrency comes into the picture, and it admits only commonly found instructions into the real computers like data movement operation and control machines. There will be some agreed upon instructions which will be counted in this RAM model. So basically a generic uniprocessor random access machine model which uses common data types. And what are these common data types? Like integer, float and other common data types. All memory are equally expensive to access here in this random access machine model, and all reasonable instructions take unit time except function call, because obviously function call is going to take a lot more time than a unit instruction. And we are also assuming constant word size unless we are explicitly manipulating the bits. So basically a generic uniprocessor model which assumes common data types, all memory equally expensive to access, and all reasonable instructions take unit time except function calls. These are the basic assumptions under which our RAM model is working. So as I have told you previously that in experimental study it is necessary to implement the algorithm. So how are we going to do here in random access machine model? Here we will analyze the algorithm without implementation. We can always use implementation, but we can use we can analyze the algorithm without implementation also. So we will be measuring the efficiency of algorithms irrespective of machine specific constants without the requirement of implementation of algorithms, and we will measure the time taken by programs which are the algorithms to be compared, and this time taken will be with respect to the input size. So algorithm here, if we are not going to implement that algorithm completely, that algorithm will be written in the form of pseudocode. Now what actually a pseudocode is? A pseudocode is a notation which looks like a simplified programming language, but it is independent of any programming language. It is a mix of common programming constructs and English language, so that everybody can understand it. Everybody who is going through the algorithm is able to understand it. And in pseudocode, we can easily count the number of those primitive operations which are there. So with the help of these pseudocodes, what are we going to measure? Actually, we will be measuring number of primitive steps that are executed except a function call. As I have already told you, other instructions like y is equals to m multiplied by x plus b, or c is equals to 5 by 9 multiplied by t minus 32, all these instructions roughly require the same amount of time. But what will be the unit of measurement unit of measurement of time taken by these primitive steps. So, how are we going? Are we going to measure these primitive steps within seconds, milliseconds, microseconds or nanoseconds? Actually not. If we include the absolute units of times in terms of microseconds or milliseconds, we will again land up with the experimental study which is dependent on the hardware and software architecture of a particular program, and we want to get rid of that dependency. That is why we will end up with the random access machine model. So, the unit to measure the time taken will be input size. So, calculating algorithm's relative running time as a function of its input size, which is normally known as n. We can also calculate the space complexity as a function of input size, and we can also calculate the time complexity as a function of its input size. And what actually this input size is, what is input size? So, this input size will be different in context of different problems, in terms of different applications, in terms of different data structures. For example, if we are taking an application or a particular example of sorting, the input size is number of items which we want to sort. If we are taking some multiplication problems, this will be number of bits which we want to multiply, and in case of graph algorithms, the input size will be number of nodes and edges. So, input size essentially depends upon the size or the problems. Now, parameters of performance measure. What will be the parameters of performance measure? We can measure time complexity, we can measure space complexity, or we can measure both, which is time versus space complexity. That means a particular algorithm, if taking a larger time, how it is behaving in terms of space, or if it is taking a huge space, how it is behaving in terms of time. So, that depends what performance measure you want to adopt depending upon your application. Which is the resource which is more important for you? Is it the time which is more important for you, or is it the space which is more important according to you? So, how are we going to measure it? The term comes here is asymptotic performance. Asymptotic performance or asymptotic analysis overcomes the problems of naive way of analyzing algorithms which were described in the experimental study. Asymptotic performance focuses on asymptotic analysis, which is a mathematical concept. Now, what do you mean by this term asymptotic? Term asymptotic is a mathematical concept which is used for describing the limiting behavior. How does the algorithm behave as the problem size gets very large? So, one thing which is very clear from here is what we are focusing upon. We are focusing upon the large input sizes. We will be calculating the behavior, or we will be observing the behavior of algorithm as the size of the problem gets very large. How that algorithm is behaving in terms of running time, or how that algorithm is behaving in terms of memory and storage requirements when the input size is going beyond a particular size. So, next comes asymptotic notations. These are mathematical tools to represent time complexity for asymptotic analysis. As we use asymptotic analysis is totally dependent upon the use of asymptotic notations. Commonly used asymptotic notations are big omega, big O and big theta. This list is not exclusive. This is only commonly used notations. There can be other notations like little omega or others also. So, asymptotic notations are used as a tool to represent the time complexity of algorithms which we are going to calculate in asymptotic analysis. Coming to the first term, which is big omega, or coming to the first tool of asymptotic performances, which is big omega. So, big omega notation provides an asymptotic lower bound on the time complexity of algorithm. This is like saying that this algorithm is going to take at least this amount of time with respect to its input size, and this is the least used notation among all the three. Why this is least used notation? Because generally we are interested in upper or tight bounds. Why we are interested in upper or tight bounds? Let us say we assume that we have given a big omega which is the lower bound. That means that algorithm is going to take at least this amount of time or at least this time, and something bad happens with the input set. That input set is totally skewed in some manner, and we are not able to achieve that big omega, and the time of the algorithm obviously increases from that big omega, and we won't be able to analyze it properly. So, big omega is the least used notation among all the three notations, because we are generally interested in the upper or tight bounds which never fails. Big omega may fails. It is the lowest bound. Let us say, for example, linear search. Linear search is a search in which we take an item and we check the array, and we are looking for that particular item which is the key element. We check the array of the elements one by one in a linear fashion, and we stop where we found our key element, and we can run the array, we can run through the array if we don't found it. So, lowest bound for linear search can be omega 1, which is possible for an arbitrary input when an element to be searched can be found at first position. That means, let us say we are looking for a key element which is available in that array at first position. With respect to this particular input set, we can say the bound for the linear search, the lowest bound, the omega for the linear search is omega 1, because we find it in the first step irrespective of the input size. But will it be true for every situation? Obviously not, because we can find that input somewhere in the middle, we can find that key element in the input at the last, or we may not find it. So, coming to the technical definition. Technical definition says, as you can see in the figure, technical definition says for all the input sizes. So, the horizontal axis, x axis is having input sizes and y axis is having the running time. So, for all the input sizes n which are greater than n0. So, here we are not considering any input sizes less than n0, and this is what our asymptotic analysis was saying, that we are actually focusing on input sizes bigger than a particular size. So, for all n greater than n0, we have a given function gn which we can denote by omega of gn. Now, this gn could be normal n, log n, n square, any function of n it could be. Now, this omega of gn is a set of functions f of n such that there exist positive constants c and n0, where 0 less than is equals to c multiplied by gn less than is equals to fn for all inputs for all n greater than equals to n0. So, here we are considering that particular area which is greater than, in which your n is greater than n0, and every time our c multiplied by gn is less than f of n. So, that is the least bound, or that is the lowest bound which is being achieved. Big omega is actually used when we want to claim the least amount of time which algorithm is going to take. It is without providing an upper bound. We are not providing the maximum bound, we are not providing the upper bound, we are just providing the lowest bound, the bound below. It bounds the growth of running time from below for large input sizes, as I have told you. So, the basic idea to understand this asymptotic notations is, this is like making a claim that one is having at least 50 rupees in his or her wallet when they really have some 10,000 rupees. 10,000 rupees are there, but I am saying I am having at least 50 rupees. So, there is a lower bound. I cannot have less than 50 rupees, but yeah, definitely more than 50 rupees I will be having, and the total actual money is 10,000 rupees. Yes, the statement is quite correct. If I am saying I am having at least 50 rupees, that statement is correct, but the statement is quite imprecise. Correct, but imprecise statement is there. Similarly, we can correctly but imprecisely say in case of a linear search that the lowest running time of linear search is omega 1. Yes, it is fine. It may take omega 1 for some input sets, and that is the least constant time that is going to be taken by that algorithm. Coming up to second notation of big O. Big O defines the upper bound of the algorithm. As big omega was defining the lower bound of the algorithm, big O defines the upper bound of the algorithm. It bounds a function only from the above, not from the below. This is contrary to the omega notation. The big O notation is useful when we only have upper bound on time complexity of an algorithm, and most of the times upper bound can be simply taken or can be simply determined by just looking at the algorithm. I will be giving some examples for this, just hold. Coming to the technical definition of big O, this is again valid for all input sizes greater than n0. So, we can define big O of Gn is a set of functions Fn for which there exist positive constants C and n0 such that f of n is always less than is equals to C multiplied by Gn. So, when a constant C multiplied by G of n, it will always cover, it will always give an upper bound to the function for all n greater than n0. That means, this is, we are saying the running time grows at most this much, but it could grow more slowly, but the running time will never grow apart from this, will never grow beyond this. This is the maximum limit for which your running time can be there. So, it is actually a blanket statement that covers all the cases, which says running time grows at most this much. So, big O notation gives only an asymptotic upper bound, not an asymptotic tight bound. It bounds the growth of running time from above. For example, let us again consider the case of linear search. Big O for linear search can be order of n, means the linear search algorithm can take time at most of order n. This cover all other cases which are below this. That's because the running time grows no faster than a constant time n. In fact, it may grow slower also. This is like making a claim that one is having less than 10,000 rupees in his or her wallet when the money available is rupees 50. One is having only 50 rupees in his or her wallet, and the claim is I am having less than 10,000 rupees. The claim is absolutely correct, but horribly imprecise. The correct claim is, yes, the money is less than 50, money available is less than 10,000, but the actual money is 50. So, the difference is huge. Claim is correct, but quite imprecise. coming up to the third notation, which is known as big theta. The theta notation bounds a function from above and below both. Previously we have seen omega notation, which bounds the algorithm growth of algorithm or rate of growth of algorithm from below, and we have seen big O, which bounds the rate of growth of algorithm from above. The theta notation bounds a function from above and below both. It basically defines exact asymptotic behavior. It is a tight bound and a real complexity class. Coming to the technical definition, as you can see here in the figure, that your Fn is actually sandwiched between C1 multiplied by Gn and C2 multiplied by Gn. So, for a given function Gn, we denote theta of Gn is some set of functions f of n such that there exist positive constants C1, C2 and n0, such that Fn is always greater than equals to C1 multiplied by Gn, and Fn is always less than equals to C2 multiplied by Gn for all n greater than n0. The above definition means if Fn is theta of Gn, then the value of Fn is always between C1 multiplied by Gn and C2 multiplied by Gn for large values of n, of course larger greater than n0. Theta of Fn automatically implies big O of Fn, and it automatically implies omega of Fn. As it is a tight bound, it also covers the lower bound and the upper bound both. When we say that particular running time is theta n, we are saying that once n gets large enough, the running time is at least C1 multiplied by Gn and at most C2 multiplied by Gn. That means running time lies between C1 Gn and C2 Gn. As long as the constant C1 and C2 exists, we can say that running time is theta n. When we use big theta notation, we are saying that we have an asymptotically tight bound on the running time. We have bounded the running time to within a constant factor from the above as well as from the below both. A simple way to get theta notation of an expression is to drop lower order terms and ignore the leading constants. For example, in an expression 3n cube plus 6n square plus 6000, we are just dropping the constants, which is 6000, and we are dropping lower order terms. So, 6n square is a lower order term here. After dropping that, we will be having theta of n. So, n here, or the function of theta of Gn here is actually n cube. So, 3n cube plus 6n square plus 6000 is equals to theta of n cube. Now, coming to the most used terms in the study of algorithms, which are worst case, average case and best case. These are actually configurations of the input which are corresponding to the slowest or fastest execution time. These input sets can be chosen as functions of n. For example, in linear search, if we have the key element at first position, that can be called as the best case. If we have the key element which we need to find at the end, that will be considered as worst case, or if we have that key element present into the middle, that will be considered as the average case. Or worst case, can one possibility, another can fall in category of worst case is we search the whole array and we don't find any element over there. That means the element is missing or the element is available at the end. Both the cases are worst case here. So, the best case, average case and worst case, that actually depends upon the configuration of input or on the permutations of the input sets in a way. So, now we have T of worst n, T of best n and T of average n, which are the times for the worst case, for the best case and for the average case, and these times can have upper bounds denoted by O of Fn, big O of Fn, and the lower bounds denoted by omega of Fn. So, here is a clear differentiation between these asymptotic notations and the worst case, best case and average case. Worst case, best case and average case are the input configurations, while your big O, big omega and big theta are the asymptotic tools to measure the running time for that algorithm. And when your omega of Fn and big O of Fn coincides, we get theta of Fn as the tight bound. So, in case of a linear search, the running time for any arbitrary input can be omega 1 or can be big O of n. It may take, for example, the element is present as the first position, it is going to take only one step, and if element is not present or element is present at the last and the total number of elements in the array are 10, that means we are going to search 10 elements and the amount of time which is taken is of order n, that is order 10. So, but the best case is theta 1 and the worst and the expected, which is the average case, is theta n. Omega n and O n can be there for arbitrary input. So, best case is when least amount of time or least amount of resources are needed by algorithm. For example, we are going for a sorting algorithm, insertion sort, and the list is already sorted in the increasing order, which is the input required. That can be considered as a best, that can be considered as the best case, and finally we get, after calculation, the time as the linear function of n. In case of worst case is the greatest amount of time or resources which are ever needed by the algorithm, achieved when incoming list or the input for in case of sorting or in case of insertion sort specifically is in reverse order. So, the time required for the insertion sort to complete this particular type of input, which is in the opposite order, will be of the form of quadratic function of n. So, worst case provides an upper bound and absolute guarantee, and average case which is expected running time, but in real life analysis average case is to be used with very care, with much of care. Coming to future analysis, now in terms of real life applications, what we analyze, for most parts we analyze worst case running time and average case running time or expected running time over all inputs, and worst case running time, which gives us upper bound on running time for any particular input. We are least interested in the lower bound because, my dear viewers, the life was actually brutal. We won't get a cakewalk in applications here. So, we may have some very weird inputs, very weird input set configurations which bound an algorithm to go to the worst case or go to the average case. It is very rare that we have best case. So, for the application real life purposes, we need worst case running time and we need average case analysis, and often these both worst case as well as average case will have the same order of growth. So, coming to order of growth, how are we going to calculate that order of growth, and how are we going to compare that algorithms without worrying about the implementation performance. As I have told you in theta thing, usually only the highest order term without the constant coefficient is taken. Let me have some examples. For example, I am having one loop for integer I is equals to 0, I less than the array length and I plus plus. We need to print a of I. That means for an array we need to print all the elements. So coming here, let me calculate all the steps. Here we are initializing I once, we are comparing I n times, we are incrementing I n times, and we are just printing that particular element which is a of I, and that too n times. So 4 times n, 4n operations plus 1 operation for initialization. So Tn, which is the time taken by this particular code, will be 4n plus 1, and order of growth will be order of n. We are dropping 1 which is constant here, and we are dropping that 4 also. So after dropping constants, the time here will be order of n. Coming to the second example, let us say we have integer I is equals to 1, I less than is equals to n, and I is multiplied every time twice, and for j is equals to 0, j cannot be more than n. So with this condition, j cannot be more than n and incremented every time. The outer loop is iterated log n times and the inner loop is iterated n times. So here total time taken by the loop will be multiplication of the two loops, which is n and log n. So Tn is n log n. Let us say in another example, we want to get the value of last element from an array, and we are aware of the length. N is the array length. So we can directly go to that particular element to access. So total time taken by that particular task or that particular algorithm is going to be 1, which is constant. In case of the matrix multiplication, this order of growth will be of size n cube. Now we have various complexity classes. If the class is constant, which is order 1 or any other constant, that means the fixed number of steps are taken regardless of input size. If the complexity class comes up as algorithm, which is order log n, that means number of steps is proportional to the log of input size. Log n is not the only constants which is available in this class. This could be log of log n or any other logarithmic based constant. Or we can have polynomial complexity class which is of order n to the power k. That means number of steps is of polynomial of the input size. Or we can have exponential, which is order of 2 to the power n or order of any constant to the power n. That means the number of steps are exponential of input size. Just to have a quick idea about how these complexity classes or how these order of growths are going to behave in real life, that means what will be the running time complexities in terms of actual clock time when these are implemented through simple algorithms. So if it is constant and the input size is 10, it is going to take 1 microsecond. Then if it is of time, if the input size is 20, it is going to take 1 microsecond, because this is a constant class which is irrespective of the input size, whether the input size is 10, 20, 50, 100 or whatever it is. Time taken by this type of order of growth algorithms will be constant, will be irrespective of the input sizes. Coming to the log n, if n is 10, this is going to take 3.32 units of seconds, 3.32 units of mu seconds. For 20 as n, that means the value of n is 20, this is going to take log of 20, which is 4.32 mu seconds. for 100 it is 6.64, and it is for 1 lakh it is 19.9 mu seconds. Coming to the linear one, which is n, with n as 20 it is going to take 10 mu seconds, with n as 20, with n as 10 it is going to take 10 mu seconds, with n as 20 it is going to take 20 mu second, and with n as 1000 it is going to take 1 microseconds. For n log n, figures are clear. The last one is taking 19.9 seconds, while for n square, which is of polynomial class, it may goes up to days. That means if algorithm is of polynomial class and the size is more than 1000, the size is 10 lakh or lakhs, it is going to take 10 lakh or lakhs to the power 2, that is 11.57 days. For n cube or for 2 to the power n or for factorial n, this may go up to gala years or it may go up to years. So, depending upon which class an algorithm is going to fall in and how much is the input size, you can calculate what time, what actual time it is going to take on a standard configured machine. Now, after analysis of algorithm, we can have how to design an algorithm. We have various strategies to design the algorithm. These strategies are brute force strategy, iterative techniques, divide and conquer, greedy approach, and dynamic programming, and many others. Other than these, we can have some graph problems in which we find some different traversal techniques, or we have some string matching algorithms which may take other than brute force techniques. Coming to them one by one, brute force is the technique which does not include any shortcut to improve performance. It will explore all the possibilities unless a solution to the problem is found. A classic example which is solved by using brute force technique is traveling salesman problem. This brute force technique is also used for naive string matching techniques. Next is iterative techniques. Iterative, as the name suggests, take one step at a time towards the final destination. We take a step into a loop until we are done, and then we will end the loop if the task is complete. So, take one step at a time, keep on repeating it until your task is complete. Example is selection sort or bubble sort. Bubble sort or selection sort place one particular element at their respective position and keep on repeating this strategy until all the elements are at their respective proper positions. Another strategy to devise the algorithm or to implement the algorithm is divide and conquer. As the name suggests, we need to divide the problem and then we need to solve it. So, divide and conquer basically is performed in 3 steps. One is divide, that is break the given problem into sub problems of the same type. Then you conquer it, basically solve these mostly recursively, these sub problems are solved recursively, and then you appropriately combine the answers of these sub problems to get the answer of the bigger problem. The classic example of divide and conquer strategy is merge sort. Merge sort is based on divide and conquer strategy. You have binary search also as an example of divide and conquer strategy. Another idea is greedy approach. As the name suggests, it at each step of the algorithm, this strategy attempts to have a greedy choice, attempts to have a best choice, and then it will find the overall optimal way to solve the entire problem. In many problems, but the problem with or the glitch with the greedy approach is, in many problems the greedy strategy does not produce an optimal solution. Example here is, to Kruskal's algorithm to find MST in a graph is based on greedy technique. Coming to the next, which is dynamic programming, it is basically, if we can see on a micro level, it is an optimization over recursion. It is a method for solving a complex problem again by breaking down into collection of simpler problems, solve those sub problem just once and store their solution using a memory based data structures. Now, how your divide and conquer and dynamic programming are different is the third step, in which solutions are stored using a memory based data structures in dynamic programming. This does not happen in divide and conquer. Here dynamic programming solves each of those sub problems just once only. In divide and conquer, this generally does not happen. Example is subset sum. The problem of finding subset sum can be solved using the strategy of dynamic programming. Just to summarize the today's lecture, we have understood what is algorithm by taking its introduction and characteristics. Then we have seen how to analyze the algorithm, what are the techniques available. Coming up to asymptotic analysis, we have covered it in very detail, covering asymptotic notations also, and we have seen various cases and examples to calculate the order of growth, and we have also taken a brief look for the design strategies of the algorithms. Thank you.